Good for me to get. Okay. I ask people to forgive the slightly informal nature of this. I'm still sort of adjusting to this new Zoom world order. So the quantum state is obviously playing an extremely important role in quantum mechanics, but of course there are long-standing traditions in physics and the foundations of physics that say that the role is in some sense not representational, that it's instrumentalist, it's pragmatic, it's epistemic. And there's clearly nothing wrong with supposing in some physical theory that some important part of the mathematical machinery of theory doesn't play a representational role. It's fine to say that the probability distributions used in statistical mechanics play some role that isn't representational. It's fine to say that the potential function in classical Newtonian gravity is not representational. But in the case of quantum mechanics, we have a plethora of results ranging from the Köppen-Specker results, Gleason's theorem, the PBR theorem, developments around the ontic model framework that collectively give us pretty strong reason to think that the quantum state is playing a representational role in our physical theories. Those reasons aren't conclusive, but they're to me at least compelling, and I think to the majority of people here assembled compelling. So I'm exploring for the moment on the assumption that that is correct. Quantum state is representational. What does that mean? Well, I think we can interpret it in a fairly minimal way. We can say that some feature of a mathematical model of a system is representational if different values of that feature mathematically correspond to different ways the system could be. So that's a sort of minimal modal way of cashing out what it is for some feature of the theory to be representational. If a change in that mathematical feature represents a change in our pragmatic goals for the theory, or a change in our information about the theory or about the system, that's clear it isn't representational. If changes in the mathematical object correspond to changes in the system itself, it's doing a representational job. Okay, that sounds kind of bloodlessly metaphysical. The reason I'm stressing that is because actually in the discussions of the interpretation of the wave function, there's often a very fast and almost unnoticed move from the wave function is representational to the wave function is real, or to the wave function is ontic, or if we're slightly more careful, to there is a thing in the world that the wave function represents. And that often happens in an almost unanalyzed way, as if it's at least the sort of basic default. We say if we want to be a realist about quantum mechanics, then that means that we're being a realist about the quantum state, which means that we're being a realist about the thing that the quantum state represents. And quite quickly, we've made moves that I want to say are metaphysically, ontologically extremely non-innocent. And the best known form of that, and the form of the title of my presentation today, is the wave function realist move, which, quote, takes the wave function literally as a physical field on a very high dimensional space. I'm going to assume that people are broadly familiar with this framework, but just to review briefly, we do non-relativistic quantum mechanics in the position representation. We know we can write the quantum state in that description as a complex valued function on the configuration space of those particles. If there are n particles, it's a function on 3 n-dimensional space. If, as is often used in illustrations, we're thinking the number of particles is something like the number of particles in the physical universe, so, or the observable universe, so 10 to the 80 of them or something, then it's a function on a 3 times 10 to the 80 dimensional space. And the wave function realist says, well, what the world is a 3 times 10 to the 80 dimensional space on which this complex field exists. And it's a field, we're asked to think, in broadly the same way as previous fields on 3-dimensional space were taken to be fields. We're sometimes even told that this is just what we get if we literally read the quantum mechanics. And I want to criticize that position in this talk from a number of different angles. Firstly, I want to say some technical things about it. I think the move from the formalism of quantum mechanics to wave function realism is not, it's not just that it's not the compulsory move you'd make if you tried to take that formalism literally. It's a somewhat tendentious move to make that gets more and more tendentious as we move beyond the regime of point particle mechanics deeper into and closer to more fundamental physics. But then secondly, I want to say, even under the supposition that those technical problems go away, if you like, even under the pretense that the non-relativistic physics is the last word, there's still something going conceptually wrong in our move to wave function realism from that sort of much more minimal representational starting point. And depending on time, I'll say a little bit towards the end of some sort of broader lessons I think we can take for how we want to interpret quantum theories from a representationalist, straight realist starting point. Okay, so let's talk about technical issues first. We can do non-relativistic point particle quantum mechanics in the position basis. We certainly can represent quantum states in non-relativistic quantum mechanics as complex functions on configuration space. As everyone knows, we don't have to do that. So even while we stay within this regime of non-relativistic point particle quantum mechanics, then there's already something slightly surprising and slightly strange that's happened. We can do quantum mechanics perfectly happily on a momentum basis. We can do quantum mechanics perfectly happily in indefinitely many bases. From a practicing physics point of view, the position basis is a convenient choice, but by no means the only convenient choice. So it's already the case that in deciding to adopt wave function realism, we haven't simply taken the formalism as is and decided to just read the physics off that formalism. We've made a substantial and not always recognized choice in how we want to present and use that formalism. And I think that sometimes gets missed in foundational discussions, partly because people are misled by the way quantum mechanics is presented at in the initial elementary introductions, and I think partly because people are motivated by the bone theory, which of course has the position representation playing a very special, dynamically privileged, ontologically privileged role. And you know, I'm in fact even happy to concede that from a Bohmian starting point, then this objection has rather fewer teeth. But then from a Bohmian starting point, the problem transforms in any case. But you know, even if one isn't uncritically adopting the configuration basis to understand the content of quantum mechanics, one could imagine giving reasons in non-relativistic quantum mechanics why that basis was peculiarly special in some sense. It certainly seems that it's a basis in which the dynamics is particularly natural and transparent. The theory wears its locality features on its sleeve. So remaining within that particular theory, you could reasonably respond to the concern I raise. But that theory is a toy. It's a powerful toy, but its expressive capacities are extremely limited. You can create simplified models of lots of things within non-relativistic point particle quantum mechanics, but if you want to do an unsimplified model of even most things that we call non-relativistic, it lacks the abilities to do that. And as we complicate the theory up and include more pieces of realistic physics, then I think things get more and more difficult for the wave function realist position. Here's a warm-up version of that. When I said that this was point particle mechanics, it's specifically point particle spinless mechanics that allows me to do quantum mechanics as a complex wave function on 3n-dimensional space. Suppose you introduce spin, suppose we're interested in electrons. Well, the wave function of one electron isn't simply a complex function on 3-dimensional space, it's a function from 3-dimensional space to a 2-dimensional complex vector space. If you pick an arbitrary basis in that 2-dimensional complex vector space corresponding to a particular direction in space, you can think that the two components of the vector represent the amplitude of the particle at a given, the relative amplitude of the particle of position having spin up or spin down. Well, that's okay in itself. I mean, there's nothing problematic about a field not just being a complex field, but being a field that takes values in some larger space. And you might think that even when I have n particles, something similar happens. It wouldn't be particularly difficult if the wave function realist, considering n particles, imagined that the function was a map from 3n-dimensional space to a 2-dimensional complex vector space rather than just to the complex numbers. But that's nothing like enough. Spin degrees of freedom can be entangled with other spin degrees of freedom, as well as being entangled with spatial degrees of freedom. If you want to follow that direction, that approach directly, then you find that the field, for let's say the 10 to the 80 particles that often get used illustratively, you find that our field now doesn't have to take values in the complex numbers or in a 2-dimensional complex vector space. It needs to take values in a 2 to the power of 10 to the power of 80 dimensional space. In other words, for each configuration, I need to give a complete, I need to be able to give complete spin descriptions for all of those constituents. Or alternatively, if you want to do it differently, you could say, well, I'll pick a direction in my original two-dimensional space, and I'll suppose that for one particle, instead of having one wave function taking values in that two-dimensional space, I'll have two wave functions, each one describing a component of the original. And now, instead of multiplying the space in which my function takes values, I start multiplying the number of my functions. So now my wave function, now instead of having one wave function, I have, where are we, 2 to the power of 10 to the power of 80 wave functions. As an aside, when people sometimes talk about wanting to read the ontology of the physics, the math doesn't care which of these ways you want to describe it. But we have an indeterminacy here between there being one fundamental entity in the world and 2 to the power of 10 to the power of 80 fundamental entities in the world. So are those forms of wave function realism viable? I'm not sure, but they're radically transformed from the starting point. And that's just when we allow for non-relativistic spin. Now let's get a little bit relativistic. We can construct a perfectly good relativistic particle mechanics, at least for free particles or particles interacting with background potentials. It's the theory you need, for instance, if you want to describe electrons in sufficiently strong magnetic fields that they had relativistic accelerations, or if you wanted to describe the inner orbitals of some larger atoms where, in classical terms, the electron gets a relativistic velocity from the strength of the electric field. That relativistic particle mechanics, however, is normally presented in a momentum basis rather than a position basis. And there's a reason for that. It's extremely difficult to construct a relativistically well-behaved analog of the position basis. And when I say extremely difficult, what I mean by that is when you start writing down quite minimal features you might want that basis to have, you rapidly prove no-go theorems. There are candidates for what we mean by the position basis for a relativistic particle. None of them are unproblematic. They don't play mutually very well with one another. Some of them don't respect basic features of how the position basis is supposed to work. Like if a particle's wave function is localized here, it definitely won't be found here. Some of them play very unhappily with relativistic covariance and with action at distance principles. None of that matters pragmatically, insofar as our experiments could probe the fine details of these things, which they can't, then the full details of the physics specifies the answer fine anyway. But if we're looking for a basis for the fundamental ontology of the theory, it's extremely unclear what a position basis here even means for for fully relativistic particles. But wait, there's more. I mentioned that we can only do that we have a perfectly well-defined relativistic particle mechanics, at least for free particles. That wasn't just a throat clearing exercise. It's been known for a long time, almost since the inception of quantum theory, that once you start trying to put multi-particle interactions into a relativistic particle mechanics, all hell breaks loose. The equations go wrong, pathological results happen, the machinery of the theory breaks down. And there's a physical reason for that, which is that doing n-particle quantum mechanics presupposes that n is just a background parameter that specifies your model, whereas when relativistic particles collide, the energies can be high enough that new particles are brought into existence. So to model phenomena of that kind, we're led out of fixed number of particles, particle mechanics, to a perspective where we can allow for particle creation or destruction. And again, there are well-known mathematical formalisms to do it. Here's an easy one. If I know what the Hilbert space for an n-particle quantum theory looks like, call it Hn. Now just take the direct sum of all of those h's, add h0 to h1 to h2 to h3, ... And now I've got a Hilbert space, a Fock space, that's well suited for handling superpositions of different particle numbers. How does wave function realism look in that framework? Well, for each of those n-particle sectors, I can represent the physics as a complex wave function on 3 n-dimensional space, ignoring spin for the moment, going back to the previous concern. So if I want, I can represent the full quantum state as a complex function on the disjoint union of 3 n-dimensional spaces for all n. I mean, that's not even a manifold, but it's mathematical. In a certain sense, I suppose it's a mathematically coherent space, but it's an infinite number of mutually disconnected spaces, such that it's possible, such that there is nonetheless a dynamical interaction between the wave function on one of those spaces and the wave function on another. So the kind of relativistic particle mechanics we end up getting out is looking like a field on a high dimensional space. It's looking like a field on a space such that defining its dimension is ill-posed, but insofar as you can define a dimension, it's infinite. But wait, there's more. The lesson that modern particle physics tends to take from those relativistic particle phenomena is not simply that particles can't be created or destroyed, but that actually particle is only an approximate emergent way of talking about what's going on in relativistic physics. In the normal language of modern relativistic physics, the theories in question are quantum field theories. The particles are certain excitations which to varying degrees need to be thought about as approximate emergent phenomena. And one way of cashing out the approximate emergent nature is that features of those particles, like their masses, their charges, in some extreme examples, even their spins, are not background parameters specified once and for all. They're dynamically variable quantities which take different values in different environments in which the particles are exposed. So the right value of the charge of the electron depends not just on some background facts about the whole universe, but on specifically which electron you have in mind and, and how rapidly it's colliding with other electrons. And furthermore, the notion of right here isn't really the philosopher's notion of true or false, it's the engineer's notion of useful or unuseful. You have a significant amount of give as to exactly what values you use for properties like mass and charge. And the difference, as far as the physics is concerned, is if you use the wrong value, the calculations get more inconvenient and annoying, not simply that you get the direct physics wrong. Okay, but there's a response one might make to that, and the response, I think somebody like the audience suspect have been biting their lip on this and cursing the mute control since I started talking about this. You might think, well, given quantum field theory, therefore the right wave function realist places their wave functional not on a configuration space of particles, but on a configuration space of fields. So a space such that each point in it pre-theoretically doesn't represent the positions of n particles, it represents an entire field across space. Well, in the first place, I think it's worth saying if that really is what people have in mind, it might be a good idea if we talked about it directly. I think a wave function realism looks very different if it's a wave function on the infinite dimensional configuration space of fields. But more importantly, that approach too runs into difficulties. I mean, firstly, while fields in the classical field configuration sense play a more fundamental role in quantum field theory, then despite the name, it's not as fundamental as all that. It's generally possible to take a given quantum field theory and re-express it in a way that leaves what's generally taken as the physical content unchanged, even while shifting it from one field description to another. So it's not at all clear that there really is an unequivocal field description available for us to get our teeth into when trying to write down a wave function realism on the space of fields. And that's related to the fact that in quantum field theory, the fields are very hard to think of as entities which are defined at all length scales. Trying to make mathematical sense of the theory, this is contestable, but at least in mainstream physics practice, trying to make mathematical sense of the theory generally leads us to suppose that it's only to be trusted mathematically and descriptively down to a certain level. So I was using the language of representation earlier, the sufficiently short distance features of the field can't be taken as representational. And then there's a fair amount of give as to exactly what kind of long distance physics and what kind of long distance field theoretic description I want to use to describe my quantum field theory. But more seriously than that, this is the point at which I'll stop this part of the talk, all of this discussion of expressing my theory in terms of complex functions on a configuration space of fields only works for certain quantum field theories. Specifically, it only works for bosonic field theories, the fields whose particle excitations look like integer spin particles. So the field underlying the Higgs boson, the field underlying the photon, to various varyingly problematic degrees, those theories can be described as wave functions on a configuration space of fields. If I have a fermionic field, that's not the case. The fields underlying the electron, underlying the neutrino, these are entities where that straightforward field configuration description of what's going on is simply not available. There are analogues. There are things called Grassmann fields. There are ways of writing things that look formally like wave functions on spaces of Grassmann fields. But in general, if you look at the details of these things, they look austerely formal. At the very least, a configuration space of Grassmann fields is a radically different kind of thing from a configuration space of ordinary, real or complex or spinor valued fields. It's not at all clear whether that even makes sense. If it does make sense as anything other than a formal mathematical construction, it's not at all clear what it means interpretatively. So wrapping up the first part of that talk, the relative simplicity of wave function realism as a literal reading of non-relativistic quantum mechanics already makes some suppressed assumptions about the way in which I present the non-relativistic physics. I use a position basis. That assumption is perhaps comparatively innocent in the context of spinless non-relativistic point particle mechanics. It becomes successively less innocent as we move into successively more realistic, more fundamental physical theories, representing, among other things, the extent to which that simple natural choice of a position basis starts eroding and abrading away, and the kind of full democracy of Hilbert space basis choice starts being more and more a feature of the, of the way the theory is presented to us. So I think simply on the technical side, I think we're a very long way from having a well-formulated wave function realism that's adequate to handle the full regime of properly described interacting fermionic bosonic quantum field theory. But for the moment, let's pretend that's not true. Let's suppose that we're considering the, well, let's first start by asking, okay, well, how should we think of the ontology of these theories if we were living in a world that consists only of non-relativistic particles obeying the non-relativistic Schrödinger equation? That question actually has a quite easy and unequivocal answer. We shouldn't think of them anyway, because the various electromagnetic phenomena that we require to live don't function in that setting, so we don't exist. So that's easy. Follow-up question. Maybe you want to ask instead, well, never mind the fact that we can't talk about that as our world. Suppose we just ask, of a fictional world in which the non-relativistic n-particle theory were exactly true, how should we think about that theory's ontology? I want to suggest that even for that situation, in that situation, the move to wave function realism is quite strongly unmotivated. And I want to show that by analogy. Let's think about the analogous question in a classical world with a similar kind of starting setup. Let's think about a classical world consisting of n-point particles interacting by some kind of multi-particle potential. How do we represent models of that theory or of that world mathematically? And the most straightforward answer is something like, well, an n-particle sector of that theory is represented by n points in three-dimensional Euclidean space. Those n points trace out paths through three-dimensional Euclidean space that represent the movement of the particles over time. And the dynamics tells us which collections of such paths are permissible and which are not. But of course, we don't have to do it that way. We can perfectly well construct a configuration space. And we can perfectly well say, instead of having n points, each of which is in three-dimensional space, I'll have only one point, it's in 3n-dimensional space. And that point by itself moves through 3n-dimensional space, tracking out all of the same information. The mathematical move from that n point in three-dimensional space to 1 point in 3n-dimensional space and back again is easy and immediate. We can certainly always do that if we want to. So suppose we were given classical mechanics in the configuration space format. Would we be well advised to say that the ontology of that theory is a single point in 3n-dimensional space? Let's stipulate that there's no absolute bar to doing so. Let's stipulate that it's not simply impermissible to do so. Would it be advisable to do so? Now, I'm hoping your immediate reaction is no, it wouldn't, but I want to pause and see if we can work out why that is. And I think there are sort of at least two reasons, or related reasons, why simply being given a physical theory in 3n-dimensional space of that kind, describing a point, isn't really giving us anything that gives us a handle on the ontology. To two reasons. The first reason I want to give, that the move is way too cheap. There's the idea of some of these strategies that we're going to read off our ontology from the physics is that somehow something about the physics is telling us about these high-dimensional spaces. But nothing in the example I've just given is actually telling us anything about the fact that the world or the system requires a high-dimensional space to represent, because basically anything can be done that way. Give me more or less any mechanical theory whereby I describe the goings-on in the theory in terms of a bunch of different complicated properties the system can have, and I can give you a state space such that each point in that space encodes all of those properties. If that's not obvious enough for the classical example, let me just quickly give an even sillier example. Let's talk about the academic progression of the undergraduates at the University of Pittsburgh. There's about 20,000 of those undergraduates, and they all have a GPA. So we can, at a crude and coarse-grained level, we can represent how they're doing academically by 20,000 real numbers. 20,000, two place decimals, I guess. And if we want to look at how academic performance on that scale tracks over time, if we want to look at grade inflation or the effect of the pandemic or whatever, we can look at how those 20,000 numbers develop over time, and we can do coarse-grained statistics. Or alternately, if we want to, we can represent all of those 20,000 numbers as one point in 20,000 dimensional grade space. And we can understand the academic trajectory of all of our undergraduates as, on this coarse-grained description, as the movement of this single point through grade space. Now, I submit it would be a mistake to look at this and conclude probably the University of Pittsburgh only has one undergraduate, and that undergraduate's academic performance is measured in a highly multidimensional way. The point is that the move to grade space was just immediate, it was cheap. I could do it simply by fiat, by saying, here is a large collection of entities, they all have relevant properties, I'll create one big space, each of whose points labels the entities with that property. So the mere fact that we're given a theory of this kind doesn't tell us anything about the theory in particular. Furthermore, I'm using the language of space when I talk about these high-dimensional spaces, but I think it's worth remembering that we're using it only in the mathematician's sense, and that sense is very thin. If you think about ordinary space, ordinary Euclidean space, or even pre-general relativity, if you think about Minkowski space-time, these are spaces with comparatively little structure. The symmetries of Euclidean space, the symmetries of Minkowski space-time, include transformations that map any point to any other point. So if I give you Euclidean space plus a point in it, I have told you nothing intrinsic about the goings on in what I've given you that I couldn't have told you by giving you Euclidean space with any other point in it. The only way I can represent highly structured information using Euclidean space is by putting lots of things on it, a whole bunch of particles or some kind of extended field or something like that. By contrast, in configuration space, the space is extremely highly structured, as represented by the fact that its symmetry group is small. Intrinsic features of most points individuate those points almost uniquely. I mean, uniquely up to the residual symmetries left from the original Euclidean symmetries on the underlying space. And that's as you'd expect, because we constructed the space to store this large amount of information. And we took a reasonably structured entity, a collection of n points in ordinary space, represented them by a highly unstructured entity, a single point in 3 n-dimensional space, and preserved structure overall through that. We couldn't have done that if we didn't drastically increase the amount of structure that was encoded in the space itself, and ditto grade space. So lesson to learn from this, or two related lessons I've learned from this. If we're given a physical theory in which the space in question is extremely highly structured, much more so in some admittedly intuitive sense than Euclidean space, we shouldn't rush to interpret that space as anything like a physical space, rather than a mathematical device to encode information about the physical goings on. And relatedly, if we're given a theory where the state is represented mathematically by something comparatively unstructured, and the limit just by a point, living in a really highly structured space, we shouldn't move at all quickly to suppose that the physical world is comparatively simple. In general, we shouldn't rush here to suppose there's a one-to-one correspondence at all between the mathematical states and the physical entities. If we did so again, if we did so in the classical case, or indeed in the grade space case, we'd be led to assume only one entity rather than a large number. Okay, what about quantum mechanics from that perspective? Well, the direct analog of the kind of configuration space realism or grade space realism would be Hilbert space realism, would be the position that actually all there is in the world is a single point, or if you prefer, a single line or a vector. It's living in a fantastically complex Hilbert space. And all of the structural features of the world are encoded by where the point is in space and not by intrinsic features of it. With the honourable exception of Sean, at least some days of the week is here. Sorry, honourable. Sean is honourable on all days of the week, but adopts this position only on some days. That position is unpopular. That sort of full Hilbert space realism is too austere for most people's blood. Jill North actually, in her defense of wave function realism, has an interesting quote about it. She discusses and rejects it, and she says, quote, "The Hilbert space formalism seems to contain too little structure from which to construct a picture of the world as we experience it. Hilbert space does not support an objective structural distinction between positions and other physical properties like spin in the way the wave function space does." But of course, the Hilbert space of any particular quantum theory does indeed permit those distinctions. Hilbert space in abstraction is completely unstructured, just as phase space is quite close to completely unstructured. But the specific Hilbert space we use for any specific quantum theory are highly structured by the particular choice of algebra of operators and their presumed relation to various spatially, temporally, or otherwise described features of the system. If that wasn't the case, then the Hilbert space formalism of quantum mechanics wouldn't even be pragmatically adequate to handle situations involving, for instance, spin and positions. What's really going on in Hilbert space is that all of the structure has been baked into into that Hilbert space structure. The space, far from not being structured enough, has all the structural goings on it, and so there's no remaining structure at all in the quantum state. It's a mere point or a mere vector. That's not quite true for wave function realism. I mean, clearly a complex function on a high dimensional space encodes a great deal more information than a single point. And so in quantum mechanical wave function realism, the representational work is being shared by the intrinsic structural features of the entity and by that entity's location in the space where it lives. But it's still the case that an enormous amount of the representational work is being done by the position of the wave function in the configuration space and not by the intrinsic features of the wave function. One way to see that vividly is to notice that all the wave function is doing is encoding quantum mechanical features of what's going on. Anything classical is encoded by the configuration space. If you ask, for instance, okay, I'll do this in Everettian language, if you suppose we're considering a branch of the wave function that's approximately classically definite, and we ask, what does the wave function of that branch look like? Well, to first approximation and modulo some subtleties, what it looks like is an unstructured Gaussian peak around the point in configuration space that corresponds to those classical details. You can change the classical details however you like, and all you do is you move that unstructured blob from one point in the configuration space to a different such point. The only thing that, quote only, the thing that's being done by more complicated wave functions, by, for instance, superpositions of such blobs, is representing quantum superpositions of classical goings on, not representing any features of the classical goings on themselves. So that makes me think that we would be right to be, we're right to be suspicious of the interpretation of the move to wave function realism in quantum mechanics, at least as an automatic move, for pretty much the same reasons we're led to be suspicious in ordinary classical mechanics. Classical mechanics is often given to us in the first time we meet it in a more conventional endpoints on three-dimensional space formalism. We're only given the high-dimensional space formalism later. Quantum mechanics, by contrast, was conceived in sin, and the theory we're given is directly formulating these high-dimensional spaces. But it would be a dangerous mistake to automatically assume, just because it is so formulated in the form we first meet it, that that has to be the most conspicuous way to understand its ontology. But that isn't to say that one couldn't give active positive arguments for wave function realism, rather than simply being led to it as some kind of automatic or natural position. But the arguments that are given, at least as I read it, don't entirely conform with the quite radical difference between the notion of space we meet in wave function realism and the notion of space we meet in ordinary physical cases. So in particular, and both David Albert and Alyssa Ney have advanced arguments along these lines, one can think that features of separability and locality are naturally reproduced on the wave functional on the wave function realism point of view in a way that isn't true if we look at other ways we might think about quantum mechanics. You might even think, and this is plausible, that there's an argument that you could argue that given the complexity of the quantum state, one's just naturally driven to represent it on some high dimensional space or other, so as to get a separable ontology. And I should say by a separable ontology, I mean something like to specify the state of spatial region A union B, it suffices to specify the states of spatial region A and spatial region B separately. There's nothing further to tell. But if you ask why do we want separable dynamics, why do we want local dynamics, it's difficult to argue for that, except taking from our starting point the fact that the ordinary physics of our manifest image seems to be a physics of separable and local dynamics. It doesn't seem mathematically incoherent to formulate theories that are not separable or local. We have plenty of examples, in fact. The argument's more going to be something like that for an intelligible understanding of the physics, or the understanding that conforms to our spatial expectations or fill in blanks, we're led to some kind of prioritizing of separability. But in the first place, the mathematical spaces on which we're trying to write a separable description are so radically different from ordinary three-dimensional space as we see it around us, that it's not at all clear what the force of the analogy is in this case. And secondly, most advocates of wave function realism, I think correctly, don't regard the three-dimensional space in which we live as illusory, but they do recognize it has to be in some sense emergent or non-fundamental. And on that emergent or non-fundamental space, we can ask, well, are our theories separable or local with respect to that actual space? And of course, the answer for exactly the reason the wave function realists already been given is no. Insofar as we're describing the separability and locality properties of our theories on ordinary three-dimensional space, then separability seems largely unavoidable. There are subtleties there concerned with Heisenberg representations and work of Deutsch and Hayden, but at least on the most straightforward ways of doing it, we're forced to separability. We're not forced to dynamical non-locality. We're not forced to fast and light interactions unless we want to adopt a non-Everettian framework, which of course nobody does. But we are driven to some kind of separable framework, and some kind of non-separable framework on three-dimensional space. And then we want to say, okay, well, given that we're anyway forced to accept non-separability on the space that was our starting point, what remains of the force of arguments that started with an understanding of separability on that three-dimensional space and move it to three-n-dimensional space? So in light of, in particular, the difficulties in the first part of the talk I was catching out with taking these notions and moving them to our more sophisticated physical theories anyway, it seems to me that the case for relying on separability here is not strong. Okay, so how should we think about the ontology of quantum mechanics then? I've been giving almost entirely negative and critical talk. Well, fortunately, for reasons of time, I won't have time to tell you in detail, which is a useful get out, but I want to say a little bit, I think, methodologically about how we might want to approach this kind of problem. First point is that thinking about the ontology of quantum mechanics is, I think, to commit some sort of category error. If I were to say, what's the ontology of classical mechanics, then if by classical mechanics I mean the entire panoply of classical mechanical theories, from point particle theories to hydrodynamic theories to field theoretic theories to classical mechanical formulations of rigid bodies to classical mechanical formulations of general relativity, and ask, okay, what are the ontology of those theories? Then you can see fairly transparently that you're not really asking a well-posed question. In some cases, the ontology of those theories is an ontology of particles, in some cases an ontology of rigid bodies, in other cases an ontology of fields, in other cases of fluids, in other cases of space-time disturbances. The best we can say at the framework theory is what, if anything, do those various ontologies have in common? So we can say, for instance, that those ontologies largely share separability. They share a feature that if I have a reasonably natural subsystem structure on my theories, then it really is the case that, because I can represent each subsystem by a phase space, and because I can represent the state of each subsystem by a point in that phase space, and because dynamical coupling introduces an interaction term in the Hamiltonian but doesn't change that kinematics, then a pair of points in that phase space suffices to represent the whole system. So there's a certain separability built into the framework of classical mechanics. And by analogy, we could say in quantum mechanics that it has a certain non-separability also built into it, at least on the face of it. The phenomenon of entanglement is ubiquitous. It doesn't rely on particular pieces of the theory. But beyond that, trying to say of quantum mechanics in general, what is its ontology, it looks like that would be making a category error of a similar kind to the error we'd be making if we asked that in classical mechanics. Okay, but maybe that's not the question we should have been asking. Maybe the question we should have been asking is, well, what's the ontology of our most fundamental quantum theory? Then we could pause and ask, okay, what do we mean by that? Well, we could be asking, what's the ontology of that quantum theory which is in fact the most fundamental quantum theory? To which presumably the answer is swift and immediate, we don't know, because we don't have that theory. If in fact you do have that theory, then I recommend that there are some more urgent scientific tasks you might want to carry out before considering its ontology. I have friends who actually dispute that as the order of what to do, but in any case, various accolades are awaiting you, which you might want to snap up quickly before going and considering the metaphysics of it. If instead you mean something like, what's the ontology of that theory we currently have, which is most fundamental, then it's still not quite clear what that means. That theory we have at the moment, which is most fundamental, is something like the Standard Model, or depending on your attitude towards quantum gravity, the Standard Model plus the Einstein-Hilbert term added to track the gravitational degrees of freedom. It's an effective field theory. It wears on its sleeve the fact that it fails at certain scales. It doesn't pretend to be a fundamental theory. In fact, intrinsic in its structure is the fact that it is not a fundamental theory. So if we were asking, ontological questions we might be asking about our most fundamental theory are not actually fundamental ontology questions. They have to be by their nature higher level or emergent ontology questions. Or instead we could be asking, okay, we could be saying, what's the ontology of any specific quantum theory under the fiction that that theory is fundamental? And I think that's probably the most charitable reconstruction of a lot of what people do when they're discussing the ontology of non-relativistic quantum mechanics. And that might be a coherent question, but there's a prior question, which is why that's an interesting thing to ask. That needn't be taken as rhetorical. I can think of a number of directions one might want to take answering that question, but it at least requires an answer. After all, at the most flat-footed level, one answer to what is the ontology of the world according to such and such fiction, the answer can perfectly well be, well, it's whatever you like, it's your fiction. At any rate, it's not obvious that the various tools of metaphysics work to distinguish frankly fictional alternatives in this way. And one answer that's at least tempting is to say, okay, the reason we're asking the question is it's a warm-up exercise. If we understand the ontology of non-relativistic quantum mechanics in this frankly fictional situation, we can warm up to understanding it in more realistic physics. But then the examples I was giving in the first part of the talk perhaps give good reasons to be cautious that processes of that kind converge. And we saw that wave function realism gets altered, if not perhaps quite out of recognition, but at least pretty radically as we move from the non-relativistic regime through to interacting fermionic quantum field theory. So at the very least, it would be rash to assume automatically that thinking about the ontology of non-relativistic quantum mechanics under the fiction of fundamentality is the route to understand deeper ontology. And I'd like to suggest something different. The ontology of non-relativistic quantum mechanics is interesting in its own right, because large chunks of the world are described at certain scales reasonably well by non-relativistic quantum mechanics. So it would be attractive to find a way of understanding what the world is like at those scales that isn't hostage to the ontology of the fundamental. If we were to get better at understanding what is the world like on scale X, in situations where such and such theory describes the world accurately on scale X, I think we might be better placed to move scale X down and get a better and learn more than perhaps we do at the moment about, quote, fundamental ontology than by this process of supposedly diminishing fictions. And the last but related point I'll make before I wrap up here is what I say of fundamentality I think also applies to cosmology. the route by which we often try to understand the ontology of quantum theories not only assumes that the theory we're considering is fictionalized as fundamental, is that it's fictionalized to be everything, to be a description of cosmology. You see this very overtly in wave function realist discussions, which tend to take n to be equal to the number of particles in the observable universe. Never mind the fact that hardly any of them satisfy non-relativistic dynamical equations anyway. It's pretty explicit in the way that the press is being thought about, that it's supposed to be thought about on the fiction that the whole universe is governed by non-relativistic quantum mechanics. This is not a framework that is well suited to asking, what is the ontology of my coffee cup, without embedding in the whole of the universe. And to some extent, of course, maybe we're forced to that by entanglement aspects. Maybe we're learning something deeper about the inherent nature of cosmology in these tasks. But I think it's worth remembering that while, of course, almost any physical theory can be thought about in some sense as fictionally describing the whole universe, hardly any of our physical theories are in fact used that way in physics. With an extremely small number of exceptions in general relativistic cosmology, what we use our contemporary experimentally successful physical theories to do is to model chunks of reality. Not just chunks of reality on some scale, that's the fundamentality issue, but chunks of reality, not the whole of reality at once. Even most of the models we use in cosmology, frankly, are used to model causal patches of an unspecified larger universe rather than the genuine totality. So to wrap up, I've said a bunch of specifically critical things about wave function realism, and I want to segue more positively to the idea that we're committing. We want to avoid the sort of category error of supposing simply because our theories our theory takes the quantum state as being representational, that we can just jump in any automatic way to saying the quantum state is real. We avoid the idea that we want to say it makes sense to talk about the ontology of any particular quantum state, any particular quantum theory. And I want to kind of encourage a way of thinking about ontology of particular quantum theories that makes peace rather more to being able to think of that theory as part of a larger whole. Okay, thank you. Apologies for some of the disorganization of that structure, and I'll stop there.
Thank you so much, David. That was wonderful. That's great. All right, I'm going to let up the participants window. Let's see. I see Alyssa first, but Alyssa asked a question last time. David Albert, go for it.
So first of all, David, thank you so much. That was, there was a lot going on there. There are a bunch of questions I'd like to discuss more. Let me just focus on be the most straightforward one. Look, and starting off with this, I'm not sure whether this is a rhetorical comment or a more, a comment, rhetorical structure of the talk, or a more substantive comment. When you were discussing the conceptual issues in the second part of the talk, you started off by saying, look, you could present classical mechanics in a higher dimensional space. You could present grade mechanics in a higher dimensional space, so on and so forth. This isn't well motivated. What's the motivation for doing this in the quantum mechanical case? So look, this was surprising to hear because, of course, the motivation that everybody mentions who's trying to defend this wave function realism, first motivation they mention is precisely a disanalogy between, say, the classical case or the grade case and the quantum mechanical case. And this is something you alluded to later on, which is there's a certain kind of representation available in the classical case. There's a three-dimensional representation that has a certain character, say separability or something like that, that's available in the classical case, that's not available in the quantum mechanical case. That's the motivation that, as far as I know, everybody who's trying to defend a view like this invariably starts with. okay? So it seems like a puzzling critique to say, oh, we could do this in classical mechanics, we could do this in grade mechanics or something like that, when of course the motivation people start with is that there's a certain kind of representation that's precisely not available in the quantum mechanical case. That is, the first thing they point to is precisely this analogy with this. But maybe that's just a rhetorical thing, and maybe that's just a way of saying it seems like the talk could have made the same point if you just skipped that section and went right to the discussion of separability that you engaged in later on.
Yeah.
But that leads to a question which maybe is more substantive.
Mm.
Look, something that would clarify these discussions a lot, I think, is to say, so people are having disputes about what's the fundamental physical space of the world on, say, non-relativistic quantum mechanics. In order for the dispute to be about something clear, people, I guess, need to bring to the table what they think of as being connoted by locutions like the fundamental physical space of the world in this or that theory, or according to this or that theory.
Yeah.
And it looks to me as if when you start thinking about these things in the context of quantum mechanics, what presents itself, but this is just a proposal, and this is a proposal for people, you know, for people to criticize, okay? It's something on the table for people to shoot at. Here's something one might think. Oh, you look into this notion of the fundamental physical space world in classical mechanics, in Maxwellian electrodynamics, so on and so forth. There are two notions that present themselves which have nothing strictly logically to do with one another. One, there is the sort of habitation of medium-sized material objects, okay? Familiar material objects, tables, chairs, particles, yada, yada, yada. Two, there is that space of points that has the feature, or the smallest space of points that has the feature that if you say what's going on every one of those points, you've said everything, okay? This is where the separability feature that you were referring to before comes in, okay? Something one might say is, one thing one might say is, gee, those are two things that come to mind when you talk about the fundamental physical space. Which one do we mean? Or something like that. Or you might say, once you notice these two features, and you notice that they're not logically connected with one another, and that in fact they come apart in the quantum mechanical case, you might say, gee, this question, what's the fundamental physical space of the world, this just isn't well posed. There were two sorts of ideas mushed together in the way we've been talking about the fundamental physical space of the world in classical mechanics and in Maxwellian electrodynamics and so on and so forth. They happen to coincide in all of those cases so that we never really noticed that they're not logically related to one another, but in fact they come apart. Once you notice that they come apart, question what's the fundamental physical space of the world becomes ill-posed. There might be all kinds of features of the habitation of ordinary material objects, like it has very little structure, as you were talking about. It has high degrees of symmetry that are maybe arguably essential to our notion of the habitation of ordinary material objects, but have nothing to do with our notion of the set of points such that if you specify what's happening at every one, you've said everything. I'm sorry, I'm already going on too long. But the thought is, look, maybe here's the way to put it into a question. You were talking as if there is even a well-defined question what's the fundamental physical space of the world according to such and such theory. Maybe the right reaction to that is that's too crude a question. That's not a particularly well posed question here.
Yeah, I mean, I have some time for that that well-posedness issue. I'm pretty sympathetic to that part of it. As for the first part, the potentially rhetorical part, well, I mean, let me not invidiously name names, but I think the position that says one simply reads off wave function realism from standard presentations of quantum mechanics gets made and is out there. And I agree with you that the more persuasive route goes via separability, but there's some rhetorical need to respond to that other part of it. It's also the case that I wanted to drive home the fact that if you, Hilbert space realism is what you get if you just very literally take the analog of the classical move. And from that point of view, Hilbert space realism is not any more automatically given to you than the classical analog. And that there's a slightly weird sort of halfway house-ishness about the wave function realism way of doing it, which as you know, has potentially a positive motivation for separability, but on the face of it is kind of strange. And I guess the only other side of that is I think just because we're presented with quantum mechanics in a way that doesn't immediately give us something like the Newtonian description of what's going on, isn't in any way a no-go theorem. I mean, there are plenty of ways of cashing out quantum mechanics that give space-time a more explicit role. They're all non-separable. Well, no, they're mostly non-separable. Those that aren't have other features that might be called pathological. So again, the desire for separability can pull into that, but it would be a mistake just to say, well, this is how we were given quantum mechanics. Therefore, there can't be any analog of the spatial description.
Okay, it's just 2 o'clock right now, so in the interest of time, I think we should thank David again. If David can hang around and stick around until 3 o'clock and be part of our large discussion, we can turn to other people's questions. So thanks again, David. And Nina, if you want to get ready to go, or if you, actually, it would be okay if we took another 2-minute break.
I was going to request that.
Okay, great. So why don't we take another 2-minute break and then we'll reconvene.